Logic modules tend to be written off by a lot of modular synthesists as just a way to derive more rhythms from clock sources, and they can be good for that, but they can potentially play a role in virtually any patch. To wit, today we're going to look at how logic can be used for sound design. The other perceptual problem with logic modules is the math part. Logic modules don't do anything by themselves. Rather, they play a mediating role in a signal path. Logic does require an extra step or two to employ, but hopefully my examples today will demonstrate that this is not really a big deal. No actual math on your part is required. One last note, for modular synthesis, logic is really an umbrella term that includes Boolean logic circuits plus a wide variety of adjacent tools that can be musically relevant. An incomplete list of the latter includes comparators, flip-flops, dividers, rectifiers, gate delays, coin toss or probability-based skippers, and even clocks and sequencers and more. They're all complementary. Most are quite simple on their own, but they enable more complex behaviors to emerge in your patches. In this video, I'm using this little module 2-bits from Clavis. This is a dual module with top and bottom sections. And each section can be set to one of a number of functions using this little pot here. Some of these functions are straight Boolean logic functions, while others are examples of those useful adjacent tools that I mentioned earlier. Each section has two gate inputs, in 1A, in 1B, and in 2B, and two gate outputs, out 1, out inverse 1, out 2, and inverse 2. So the second gate outputs always do the opposite of whatever the first one is doing. So if out 1 is low, inverse 1 is high. If out 1 is high, then inverse 1 is low. Same down here. Also, the second input on the lower half, where it has the red text, this can take fluctuating voltage, things that aren't just high and low. And that is used in a handful of the functions, the ones in red, and you'll see a little bit more of that later. Now let's look at some sound design patches. I'm keeping these patches simple. Each is a springboard for further exploration. I've built all the patches around a basic keyboard-controlled voice, oscillator into filter into VCA, and I'm pulling the pitch and gate from this key step. Here's what it sounds like on its own. It's usually obvious how to make things happen while a note gate is high, whether from a depressed key on the keyboard or from a sequence. But what about the other times, such as during the release phase of a note event? There are quite a few ways to attack this problem, and you can probably find another way to patch this one up, but you probably can't find a simpler way than with NOR. NOR is the inverse of OR. So if we take a molt of our gate from the keyboard and we patch it into the input on the top section and set it to OR, we can see the OR circuit go high when I press a key, and then low when I let go. That second output here, which is the opposite of the first, is giving us the NOR result. So it's high, like now, when no key is pressed, and then when I press a key, it goes low. To show this in a patch, we're going to start with our basic keyboard controlled voice. Then we're going to molt our gate signal to OR, and then we're going to take the NOR output to the CV input on a second VCA. Then we'll patch a clocked random sample and hold to the input of that VCA, and finally patch the VCA out to modulate the FM input on our filter. As an aside, I am deliberately mimicking the patch diagram of Monotrail's Tech Talk videos, which you're hopefully already familiar with. If not, you should definitely check out his YouTube channel, which has some of the most consistently excellent modular synthesis tutorial content out there. So here I'm going to now plug in the cable that connects the NOR output to our VCA, and we can hear our patch in action. So during that release phase of each note, right now, we hear the sample and hold modulating that filter cutoff. Of course, we don't have to use sample and hold as our modulation source, and we don't have to use filter cutoff FM as our modulation destination. The possibilities are endless, and it's really just up to your imagination and the modules at your disposal. One way to make a voice more expressive is to introduce behaviors that only happen part of the time. Probability-based gate skippers can be a handy tool for this purpose. For this patch, we're going to use the random function in the lower half of 2 bits. This is a function that has a parameter, the probability setting, which is the rough percentage of the time that a gate will be allowed through. So to set that probability, I need to press the set button, and its little LED there will light up, and then I can reuse this knob to make a setting. So before I do that, I'm going to plug in a molt of the gate from this keyboard, and if I set the probability all the way counterclockwise to 0, then I can sit here and press keys all day long, and you're going to see no activity down here at the outputs. If I turn this all the way clockwise to what is 100%, then every time I press a key on the keyboard, you're going to see activity. You're going to see that our main output goes high and our inverse output goes low whenever I press a key. Now I could put this in the middle, and now it's going to about 50% of the time you're going to get an active result where the gate passes out of the main output. It's random, but it's probability based. Now I also could patch an external CV into this jack because it's one of the red features here on the faceplate, and I could use that external CV to modulate this probability. But for now, I'm just going to manually set this to somewhere around 25%. Now to show this in an actual patch, I'm going to start with the basic keyboard controlled voice. I'm going to molt the keyboard gate to the gate skipper, which is labeled random on 2 bits. And then I'm going to patch the output of the gate skipper to trigger an envelope. And then I'm going to finally patch the envelope output to the fold input on my oscillator. Here I'm patching this cable to the output, which leads to trigger the envelope that is going to modulate the fold parameter on my oscillator. So I'm just going to press play on the sequencer. Hopefully you can see here that occasionally, about 25% of the time, a note will pass its gate through the gate skipper, or the random feature on 2 bits. And when it does, you hear the folder in my oscillator wavefold the sound of the note. I can play around with, since we're still in the parameter mode, I can play around with this. I'll turn it up. If I go all the way, every single note is going to be folded. At 0, none. So I can set it to taste. Of course, we don't have to be triggering an envelope with this, and the envelope doesn't have to modulate a wavefolder. The possibilities, again, are endless. Our earlier example using NOR logic gave us a really easy way to target something that happens at the end of a note. But it does so by giving us a gate that lasts as long as the time between the note that just ended and the next note. In some situations, that long gate is not so convenient. A function that detects a rising edge, a falling edge, or both can offer advantages. The top half of 2 bits has all 3 of these 3 edge detection options. Again here, I have a molt of our gate, which I'll put into the input. And I'll choose the first of our edge detecting options, which is the rising gate. So if we pay attention to the LEDs here, when I press a key, you're going to see a gate happen, and then it ends. And when I let go of the key, nothing happens. If I switch over here to the falling edge detection, when I press a key, nothing happens, but when I let go, we get a gate. Lastly, in the both rising and falling edge detection mode, we get a gate when I depress the key, and another when I let go. The duration of that gate is something that you can set manually by going into the set mode and then adjusting this pot up here. All of the values on the left are very short, and the shortest would be something like 1 millisecond. So we're going to barely see anything happening there. And then at its maximum, it's up around 10 seconds, which I won't choose, but I'll choose something a little different and a little shorter than that, and you'll see we get a nice long gate there. To show this in a patch, again, we start with our basic keyboard controlled voice. You molt the gate from the keyboard to the input as usual on the logic module, but then we're going to patch the logic module's output to the strike input on a low-pass gate. And I'm going to patch a noise source to the input of the low-pass gate, and finally patch the low-pass gate's output to a mixer where it can be combined with our main voice. So this cable leads to the strike input on our low-pass gate. I'm going to plug it into the output. I'm in the rising edge detection mode. So when I press a key, we're going to get a quick pulse out of this, which is going to strike the low-pass gate and give us a percussive element. If I switch this here to the falling edge detection mode, we're now going to get the same percussive element, but it's going to be at the end when I let go of the note. And in the both mode, we get of course, we don't have to be striking noise in a low-pass gate. We could be triggering samples, envelopes, or any number of other things. For our last example, we'll move beyond the keyboard gate and use a comparator to determine when something special happens. The lower half of 2 bits includes a comparator. It's the option labeled comp. And you put the voltage you want to test in the second input, the CV input. This would be a continuously variable signal, something like this, which is the pitch output from the keyboard, a molt of it. And I'll fire up the sequence. And we now need to adjust the threshold of the comparator. So I'll go into the settings and then we'll adjust this knob. And what we're basically looking for is the beginning of some activity here. Oh, there we go. So what's happening is when the voltage here is higher than the threshold I've just set, then this gate goes high. When this voltage is lower than the threshold, it goes low. And we get the opposite out of this jack here. So let's do something with that. In this patch, I'm going to start again with our basic keyboard controlled voice. I'm going to molt the pitch from the keyboard to the CV input on the comparator. And then I'm going to patch the output of the comparator to an effects send, so that when the comparator gate output goes high, the audio from our voice is sent to a digital delay. This is our pitch output as before, running into the comparator. And this here is my effects send. So I'm going to put that in the main output. And I'm going to fire up the sequencer. So what we hear is that the higher notes in the sequence are getting sent to the digital delay, but the lower ones are not. I can adjust this, so if I make it higher, nothing gets sent to the delay. If I bring it low enough, everything gets sent. You can see that the gate is just high because at this point my threshold is below the pitch values on this CV. But I'll now bring it up just enough there. We're starting to see some change here. I'm going to bring it up a little higher. And now we're back to just the high notes getting sent to the effect. Now if I wanted to switch this around so that only the low notes get sent to the effect, that's when I would use the inverse output. So I'm going to pop this out and stick it in the inverse output. And I'm going to lower the threshold a little bit. Adjust it, and now just the lowest notes are getting sent on to the digital delay. Let's try something else. instead of the pitch output, I'm going to bring in the velocity output from the keyboard. I'm going to go back to our main output for the effect send. So here, I'm going to play some notes. So we're using the comparator in this case so that only the high velocity notes that I hit on the keyboard get sent on to the effect. But when I play more gently, then those notes are not sent onto the effect. Of course, opening effect send is just one of the possibilities. For that matter, instead of pitch or velocity, you could be using any other signal into the comparator, even a randomly fluctuating one. That's it for now. Hopefully these examples have given you some food for thought, and Logic is now looking a little easier and a little more generally useful. Happy patching!